Good afternoon, everyone. It's 1 o'clock, so we're going to go ahead and get started. Welcome to the webinar put on by the HBM Academy with the topic of measurement cables and shielding. Our presenter today is Clark Anderson. Clark has 10 years of experience as an automotive test technician and then joined HBM to work as an applications engineer, doing technical support and helping customers use our equipment. Clark, it's all yours.
Well, welcome to the Measurements, Cable, and Shielding webinar. Once again, my name is Clark Anderson, and I'm the application engineer here at HBM. So, to start off this webinar, I guess, what is our problem? And the problem we have is sensor measurements can be subject to noise interference. And this noise can result in inaccurate measurements, and in severe cases of noise, it may be impossible to detect your actual measurement signal. So to solve this, we want to reduce the noise interference, and to do that, it helps us to actually understand what the possible noise sources are. And secondly, we want to have a proper measurement cable and use proper measurement techniques to help reduce these noises. So today's webinar, we're going to cover measurement cable basics. We will also discuss proper measurement cable shielding. We will discuss noise sources, and then also noise reduction techniques and best practices. So we talked a lot about a measurement cable already. The question comes up, what is the measurement cable's purpose? Well, it kind of has four basic purposes. Main purpose is connection between the sensor and the amplifier. And so it carries the excitation voltage from the amplifier to the sensor. And then it carries the measurement signal back from the sensor to the amplifier. And then, really regarding this webinar, it's a protective function against interferences. So, if we look at the simplest case of a Wheatstone bridge circuit, you'll see there's 4 lines are required to connect to the Wheatstone bridge, and 2 of them are for the excitation, and then 2 are for the measurement signal. You'll also notice in this diagram there's some dashed lines, and the reason for that is there's also a 6-wire circuit. In most HBM classic amplifiers support the 6-wire circuit, and so I just wanted to touch on it because we'll show you some 6-wire cables. But these sensors here that make up the extra 2 wires, what they do is they measure the excitation voltage at the bridge such that a compensating circuit in the amplifier can adjust it so that any lead wire resistances have been accounted for, and that you have the actual excitation voltage at the bridge you desire. So, a little background on our measurement signal. We will hear people talk about a signal-to-noise ratio in measurement, and the basic story is if you have a large measurement signal and a small noise signal, the noise is not going to cause you much problem. But if you have a very small measurement signal and a correspondingly similar sized noise signal, then it becomes where you can get inaccurate results, or just it's difficult to determine what is occurring. And so if we look at a typical load cell that HBM supplies, they have a 2 millivolt output. At nominal rated force, there's 2 millivolts a volt. If we set our bridge excitation to be 5 volts, then we will get a maximum signal voltage from the load cell of 10 millivolts. So if we take an example, if we have a 100,000 digit resolution amplifier, that means we'll be able to resolve 0.1 microvolts. So if we compare that 0.1 microvolts to the 10 millivolts, it would be similar to comparing the thickness of a TV case, which is 3.2 millimeters, to the height of the Eiffel Tower, 320 millimeters. So you can see that we can resolve a very small signal, and of course a small amount of noise could override that. So this is where noise becomes very important. So where does noise come from? Well, electromagnetic environmental pollution has grown steadily over the past years, and it places increasing demands on the immunity of our electromagnetic disturbances of our measuring equipment. So some of these sources are AC power lines. We've got motors, and then motor starters also, transformers, relays, generators, rotating and reciprocating machinery can cause noise. There could be magnetic field present. If you're near radio equipment, even mobile phones. Welding equipment can cause noises. And then finally, we'll briefly touch on thermoelectric voltages. So, if we want to summarize quickly, basically we say electrical noise can be categorized into two main types. First being electrostatic, and the second being magnetic. So electrostatic would be alternating electric field, which, so you're going to have your main power lines, and just real AC power lines. Magnetic, it can be a flow of electric current, or it could just be magnets. So if you think of an electric motor, it's going to have current and magnetism. And what you'll see is most noise that you would pick up is actually a combination of the two. So unless you're in an ideal environment, you're not going to see just one or the other. You'll see a combination. And you can see here in the little diagrams that noise can be radiative, inductive, conductive, or even passive transmission. So, and they require different countermeasures, which is important. But we will cover that here shortly. And then, as I said, there's an additional source of noise that can occur with these different materials, and those are thermoelectric voltages. So, if you imagine a copper cable here is our sensor cable, and typically you will solder your cable to a connector, and so you'll have copper cable to solder, and then either gold, silver, or aluminum pins in your connector. And the junction between those dissimilar metals can cause thermoelectric voltages. But if we look at where those noise sources can be, the one thing about thermoelectric is they tend to be down near 0 hertz. So those can be easily filtered out, really. And if you have really good connectors, they're minimized. But you'll also see that a real typical noise source is 60 hertz AC, which is typical here in the United States. You can see that from your lights, the power lines. But of course, you can also have the harmonics of that. And it will generally drop off as the frequency increases. But so the important part about this is if you look at the spread, we can see where they are. And today we're going to cover two types of excitation for amplifiers. One is being DC, and the other is AC, carrier frequency amplifier. And so if we look at the transmission response of a DC amplifier here on the left side, you'll see that all frequencies are passed up to the cutoff frequency within the amount of taper there. But you'll see what this means is that there's thermoelectric and then those 60 hertz in the harmonics will be passed into your amplifier and be measured. Where a carrier frequency amplifier, what it does is it has a very narrow band pass centered around the carrier frequency of the amplifier, and typically those are much higher frequencies such that the thermoelectrics and the 60 hertz and harmonics are avoided. So this will be important here a little later on when I show you some noise examples. But just overall quickly is that an AC excitation amplifier has very good noise in it. So we're going to go over some examples I created, and what I did is I just used a right angle grinder, to buy any hardware store, and it plugs into the wall here. And so the setup of my measurement was I used an HBM NGC Plus, and I had DC excitation. I'm using a 3-wire quarter bridge strain gauge setup, and it's 350 ohm gauge. So it's a real common measurement here in the US. On this little demo that I did, the lead wires to the actual strain gauge are not shielded. So which would be very typical when you're running strain gauges. The small lead wires up to it are usually laid in parallel and are generally not, likely not shielded, maybe just have a covering region. So what I did is I took the right angle grinder and I pulsed it on and off, and it created these large noise spikes you see here. And you can see that the peaks went up to 12 micrometers a meter. Well, it's not a large amount of strain, but compared to the I guess, room noise that was present is, orders of magnitude higher. So this green area that I've highlighted, what we're going to do in the next slide is look at an FFT of that. And this is what I call the room noise. It was done here at my desk in my office, and I have lots of equipment around, so there is going to be some noise. And as you can see, the 60 hertz frequency is the biggest contributor, plus it's harmonics. So that's with those unshielded strain gauge leads, I'm picking up some electrical noise here. But if you look at the scaling for the y-axis, it's a very small amount of noise. So it's typically it wouldn't be a problem unless you were trying to resolve 5 or 10 microstrains. So now this slide, this green area here, this is a zoomed in section of one of those spikes created when I pulsed on the grinder. So for this next slide, we're going to look at the FFT of that. And as you can see, once again, there's a 60 hertz component, but then there's a very large 180 hertz. And I don't know too much about the specifics of the grinder itself and what it would create, but the key point here is the magnitude of the Y scale now is orders of magnitude higher. And to simplify the comparison, I plotted the two FFTs against each other. And you can see the blue trace here is with the grinder being pulsed on. The red trace is what I kind of going to call like the room noise. And you can see the scaling on the y-axis is the log scale. And you can see there's more 60 hertz noise when the grinder's on. It's an example of how if you didn't know I was pulsating that grinder, you may mistake it for strain in the actual gauge. So this is an example of if you can remove noise sources, if the grinder is not in the area, then you can really eliminate some noise. So along that, let's talk about how can we reduce electrostatic condition. So the first thing is we want a good conductive shield. And there's typically two types of shield types used in transducer cabling. There's braided wire, which has 95% coverage and very low resistance. And then the second type is a foil shield, which gives 100% coverage, but has slightly higher resistance. So, along with this shield, you need proper grounding for your shield, and you need to have your shield ground connection solid, or you don't need to, it shouldn't be intermittent. And all of this, you want a Faraday cage. When you see here this image here, the person inside the Faraday cage is unaffected by the electrostatic discharge. What the Faraday cage does is it basically allows this discharge to go around the exterior and then out the ground wire. So, and what HBM has done is we have what we call an HBM green line concept. So, with HBM green line concept, what it is the complete measuring chain is fully enclosed in a Faraday cage through the design of the cable shield. Here the Faraday cage is represented by the green lines, and you can see that it fully encloses the transducer, the connection from transducer to the terminal box or connector, and then from there to the amplifier, and once again it is on the amplifier. So typically transducer housings are made of metal, and then also amplifier housings are also metallic, designed to create their cage. So all of them need to be, all the components in the chain need to be surrounded by a closed EMC tested shield. And the shield transitions should be solid and realized in the form of flattened, closed, and low impedance joints. And this is ensured if you use original HBM connectors. Now there can be problems with Faraday cages, and this will be a very common theme with noise. Just noise, because one solution works in one area does not mean it will always work in another. And generally troubleshooting noise tends to be a trial and error exercise. So, as we said before, use the Faraday cage. Well, there are problems that can occur. And one of them is if there's potential differences, the compensating currents will flow across the cable shield, and this typically will cause a 60 Hz interference. So a solution to that is to connect the transducer and amplifier with a potential compensation line. Usually we would recommend a highly flexible stranded wire of 16 millimeters squared copper. Alternatively, you could separate the shield on one side and bridge with a disc capacitor. So, I'm talking about the requirements for a good connection of our shield. So, EMC compliant wiring requires that the signal ground and shield be separate. So therefore the shielding can be connected to earth at several points. So to the amplifier housing, to the sensor housing, or other ways. And if we look here at a HBM connector, you can see on the right side we've got a transducer cable coming in. Then we have a strain relief. And underneath that strain relief, you just make it out with a braided shield. And so the shield is grounded to the connector housing through the strain relief. And then you see the housing itself is a metallicized plastic here connector, which provides a Faraday cage around there. And then the connector connects to the amplifier and completes the Faraday cage. So we need to have the same kind of connection of our shield on the sensor side. And typically what we do is You can see here in the yellow color we have a braided screen, and that braided screen goes into the sensor housing and through a ground sleeve it's flattened and connected. And then the sensor housing once again creates a Faraday cage, and this will give us good EMC protection. So, if we want to look at the structure of a measurement cable, this is a 6-wire cable, and I talked about HBM uses 6-wire amplifier source a lot. So, what we have on the outside is we have a sheath. Typically, this is a PVC rubber type material. This is used to protect the internal wires from environmental contaminants, like oil, solvents, whatever. And then just abrasion resistance. After that, we will have the common shield, which is a shield that encompasses all our wire pairs. And this is either, once again, a braided wire or a foil shield. And then each wire pair, those are shielded also. So there's a additional shielding there. And if we look at one of the wire pairs, so each wire has an ohmic resistance, which is dependent on line length and wire cross section. So each cable and the capacitor and the electrically conductive areas are separated by insulation. And this is an effect that cannot be avoided. However, it's possible to ensure by means of cable structure that the capacitance remains small and symmetrical. And the symmetry is also achieved by twisting the wires in the cable sheet. And a guideline is about 5 twists per meter. So, it's very important to use quality measurement cables. And this slide here, I show the different cables that can be ordered from HBM. And the reason this is important is if you are in a low noise environment, well, then you can get by with a less noise resistant cable. But if you're in a severe noise environment, you think like manufacturing or just anything with lots of noise, then you need to buy a higher quality cable that has more noise immunity. And you can see here the way our part numbering works is the dash number indicates how many wires are in the cable. So on the top left, we've got a 3-wire cable for a quarter inch circuit. And this rule of thumb would be the more noise immunity a cable has, the more the cable costs per meter. And that's why you just have to make kind of a decision on what your noise environment is. You can see here the lower right corner, this KAB800 is a quad shield cable, twisted in pairs. It's suitable for very long distances with CF amplifiers. And that's the actual cable I showed before, cross section. Now, sometimes it's necessary to have a cable extension. If you buy a sensor from us, typically you would have a 3-meter cable, but you can also order sensors from us with special cable length. But if you don't want to do that, or you already have a sensor, you can also just put in a cable extension. And so you can either do that via connectors or have some kind of terminal box. If you're using the HBM 6-wire amplifier, we suggest using the 6-wire extension cable. If you're using a 6-wire amp and you only have a 4-wire sensor, one thing to note is the feedback bridges should be connected on the sensor side of your connector. The reason for this is it will any transition resistances in the plug will be corrected. So we just like to talk about electrostatic noise. Now we're going to talk about electromagnetic noise. And remember, once again, I said that most noises are a combination of the two. But here's some data I collected, and this data was created using two handheld magnets, and it's created a magnetic field around the cable. This is recorded using a Quantum X MX840. This is on DC excitation. I used an HBM C9B load cell 500 newtons, and it comes with a shielded cable. Now, one thing I did here is I coiled my cable in the middle. I think I did 3 loops, and then I took my magnet and I moved the magnets back and forth to create an alternating magnetic field, or a changing magnetic field. And you can see all these spikes in this data. With the largest one, I was able to create a 21 Newton signal in engineering unit. And so if we look at that versus our nominal rating of 500 newtons, that's a 4% error in our signal. Now, what I did was probably not very common, especially at test labs, but you need to be aware that magnets or magnetic fields can really cause a signal distortion. Because once again, I said this load cell had a properly shielded cable, or the proper Faraday cage. So the next thing I did is I uncoiled my transducer cable. So this is the same test, but with the cable pulled straight. And as you can see, I was not able to generate that 21 Newton signal, just about 5 here. So now my error is only 1%, which is a big change. And all that I did was to straighten the cable out. This highlights how important cable routing is. It's always best to have a central cable the exact right length needed. Now, that's not always possible, especially if you have a load cell with a preset length. But the key is you shouldn't coil it up in the loops when you have extra. Now, this chart here, you can see that there's no spikes here. What I did here is the MX840 has an AC excitation option, which is actually what we prefer to use. And even with the cable coiled, I was not able to induce any spikes from the magnet at all. So, you can just see here that the noise there is just wind noise, and it's very small. So, I talked a little bit about AC and DC excitation, but go back over it again. AC excitation has very good noise noise. And it's because the AC excitation's narrow bandpass characteristics, so the receiver is only interested in the carrier frequency signal and not other frequency signals around it. So that this causes electrical noise to have a very limited effect on measuring results. This is even true in extremely harsh environments like high voltage engine systems, AC power lines, or railway systems. This unit also allows high quality measures even in common dirty power environments that cause problems with standard DC excitation. However, it needs to be noted that this carrier frequency here of the quantum unit is 4800 Hz. If there's a 4800 Hz noise signal in your environment, it would pass that and it would cause lots of problems. Several of our amplifiers are able to come with different carrier frequency excitation. So if you do decide to use AC excitation amplifiers, you need to make sure you select a carrier frequency that is not a common one used in your environment. And you see here in the charts that the magnetic noise, FF2, most of the energy there is 200 or 400 Hz or below. which is far outside of the 4800 hertz pass-through range. So, in addition to using an AC amplifier, other methods to reduce electromagnetic noise, careful routing of wires. I showed how having the cables looped versus straight has a dramatic effect on the noise, even when using properly designed shielded cables. So the other thing we want to do is we want to ensure that noise voltages are induced equally on both sides of the amplifier input. And so you also want to use an amplifier with a good common mode rejection ratio. And you see here examples of twisted pair wires. When signals are sent down twisted pair wires, when one wire in the pair becomes positive and the other wire becomes negative by the same amount, any of the wires near this pair will be affected by the crosstalk, and if the sum is zero, then the effects of the crosstalk will eliminate. So it's important we have equal length wires. If you lay your strain gauges such that with a longer distance to, like, say, half the bridge versus the other half of the bridge, you should still use the same length wires. But don't coil them. An example of some poor cable laying. If you're in an industrial environment, you're going to have lots of mains power cables here. So the mains power cable and the measurement cable should never be laid in a common cable channel. It must be ensured that the measurement cable at no point is laid in parallel to the mains cable. You need to ensure clean separation, especially in control cabinets. So the correct way to do this would be to have at least 50 centimeters of distance between the measurement cable and your mains power cable. If you have the need to have your measurement cable cross over a mains power cable, if you can do it at 90 degrees, this would give the smallest influence on the electric and magnetic field. So, try to avoid crossing it not angle less than 90. Now here I've got a picture from an HBM installation, and it's a temporary setup, but it allows me to show you good and bad examples. So you can see on the left side, that's proper cable routing. You see it's coming out of the shield over where the actual gauge is placed, but you see the cable is laid nice and straight and away from other sections. And then on the right side, you'll see that the extra cable here is coiled up. Now, I've already demonstrated how bad that is. The note here is that this cable is coiled up just as a temporary solution, because this tower here, it's not in the test location, and once this tower gets put in the test location, then it will be, the cable will be properly routed to the back position unit. One thing to note is if you use HBM load cells, up until 95, it was common to not connect the cable shield with the transducer housing. And this was to avoid ground looping. However, this shielding concept is no longer applicable because of CE/EMC regulations. And they required interference in either 10 volts or meter, and the only way that can be realized is on a shielding concept based on the Faraday cage. Therefore, any HBM load cells after 96 will have the shield connected to the sensor housing. I'm not sure what other manufacturers are doing, but if you use HBM load cells, just make note of that. So, in summary, you want to have a good Faraday cage and conductive shield. You want to do correct cable routing. I showed you examples of how Improper's unshared cables and also poor cable routing can induce noise into your signal. You want to have an amplifier with a good common mode rejection ratio. You want to use twisted pair cabling. If you can, remove your noise sources. I mean, that's the best solution, but that's not always possible. Make sure you have proper grounding. If you don't want to have any different ground potentials, you want to have solid contact, as the loose contact will actually introduce noise. If you can, use AC excitation. I showed how using AC excitation eliminated that magnetic noise. And then, of course, it's not always possible to eliminate all noise, and so all noise can be a measurement, but post-process you can do both. And that'll be covered more in a future webinar. So if you have, from more sources of information on these similar topics or this one, or training sessions or app notes, they're all available at www.hbm.com. If you have any questions, you can email support at usa.hbm.com or call our technical support at 1-800-578-4260. So thank you, and if you have any questions, right now you can actually type them into the WebEx Q&A dialogue, which is in the icon at the WebEx store. Thank you.
Thanks, Clark. So if anyone has any questions, they're welcome to